Okay, so here's what we're up to. Vector addition of forces. We need to go through how it is that if you have individual forces, how do you get the overall or net force, as we call it, from them? So I have two forces. They're of size 3 and 4 newtons, but they'll point in various directions, and that's very crucial for how the result ends up coming about. By the way, I should also mention that vector addition of forces is the topic of your lab this week. So this will be basically what you might reference there. If the two forces happen to point exactly the same way, they are perfectly reinforcing, then you can just add 3 plus 4 to get 7 newtons. Your overall or net force is 7. But in any other case, adding up the sizes of the forces without any regard for their direction is going to give you a bad result. For instance, if these forces are exactly opposing each other, then you only have a net force of 1 newton, because 4 newtons one way, 3 of them get taken away, so there's only 1 left over. You could have that they're 90 degrees to each other, because if you're pulling on an object, you have the option to pull lots of different ways. One of the ways you could pull on it is with two forces which are not directly with each other, not directly against each other, but 90 degrees. So last time we showed that the net force here would be 5 newtons. And the reason we could do that is we could pretend like the 3 newtons was the x component and the 4 newtons was the y component, and then by Pythagorean theorem, you get that the force is 5 newtons. But that's just kind of a workaround when you get lucky that the two forces happen to be either with each other, against each other, or exactly 90 degrees. If these are truly independent forces, you can pull on things in the most general ways, right? You could have the two forces act like this. And we need a prescription for how we're going to find the net force if they pull like that. So just for the sake of argument, let's say we have the 3 Newton force and the 4 Newton force pulling at angles like that. And let me just make up numbers. Let me make up a number that the 3 Newton force pull, let me reference both of their pulls from the that horizontal line. Let me say that F1 is 3 newtons, 30 degrees above horizontal. So that dotted line I sketched was the horizontal. Let me suppose that F1 is 30 degrees from that. And now notice I did include the vector hat because I'm saying here's the size and here's the direction. And then let me suppose that force 2 is 4 newtons at, that looks like a bigger angle, let's call it 60, right? So how might we add those two together? So we need some prescription for adding these two together. And as you can probably imagine, we cannot just say it's 7 newtons at 90 degrees. That doesn't make any sense, okay? We can't just add up the columns. We need a prescription for how to do this. So here is my prescription for how to do it. I'm going to actually do the exact same thing that I do with components, right? With components, we learned, if you want to reassemble them, you put them head to tail, right? And that will form a nice 90-degree triangle. We can do that here too with what I'll call the graphical method. So the graphical method of vector addition is to, again, put the individual vectors head to tail. Just like I did with components. I put the individual vectors head to tail, and then I'm going to connect the tail of the first to the head of the last, and that's going to be what I'll call the resultant. The resultant because it's the result of my sum. It's, in my case, I'm adding individual forces, and my resultant is my net force. So let me do that. It seems like an appropriate prescription. The same way that I add up vector components, I'm going to now add vectors themselves. And it makes sense because components are kind of like mini vectors, right? component, an x component is like a little mini vector that has only a choice of pointing along the plus or minus x direction, right? Components are vectors. They're just that are vectors that are part of a bigger vector, right? So let me do that here. I'm going to add my 3 newtons at 30 degrees. And then I'm going to add it head to tail with my 4 Newton force at 60 degrees. Now notice that when I put them head to tail, I did not change anything about the vector that is important. I can't decide to make the vector shorter, so if it's longer, then it has to stay that length, right? The length or size of a vector is an important thing. And I didn't change the direction. So notice that if the vector pulled like this over here, okay, then I just picked it up and moved it over here and put it head to tail. I did not accidentally pick it up and go, whoops, so it points over here, right? So it's important when you put them head to tail that you preserve whatever direction they're pointing, right? Because the direction is an important thing about a vector. So this is still 60 degrees above horizontal like it used to be. I've just drawn it in a different place so that I can put them head to tail. So let's go ahead and follow the prescription. I connect the tail of the first to the head of the last. There is my net force, or resultant. My resultant of my sum, which in this case, since I'm adding force vectors, I get the net force. Now you're going to be trying this out in lab yourself. You're going to be trying out the graphical method. Here's the only problem. If we were doing components and reassembling them, we're guaranteed to wind up with a right triangle, right? Here we are not, okay? These two forces happen to not be 90 degrees from each other, which is fine, right? These are individual forces, and you're entitled to pull on an object however you want. So in this case, we did not wind up with a right triangle, and we do not have access to all the right triangle math that we would normally have. You might still be able to knock this out with some kind of, trigonometric theory, right? But this is not a nice triangle. It's not a right triangle. It's not an isosceles triangle. It's not an equilateral triangle. It is the most general triangle that you could have, right? So it seems like maybe thinking of it as a triangle is not going to be as easy here. Now, even if you could somehow use like the law of cosines or law of sines or something you might remember from trig to get that size, that's not going to be a payoff in the long run. Here's just 2 forces that I had, right? What if I had 4 forces? I put them head to tail. 1, 2, 3, 4. And now I have to connect the tail of the first to the head of the last to get the net force. That's a general 5-sided object. How's your generalized pentagon theory? I know mine is terrible. Okay, so there's got to be a better way. There is. Okay, because here we could potentially have 2, 3, 4, 5, 17 different forces, right? So we need a better way to figure out the result. Okay. Now, how are you going to try the graphical method out in lab? What you're going to do is you're literally going to treat it like a little experiment. What you're going to do is you're going to very carefully sketch this with a protractor, making sure it's the right angle that you want, 30 degrees or whatever, okay? And then sketch this one out and measure with a protractor and make sure that it's exactly the angle you want it. Then you're going to pick a scale for how many newtons is represented by how many centimeters. Now, of course, there's no equivalence between newtons and centimeters, but that will allow you, if this is 4 newtons to 3 newtons, it'll allow you to draw these two in the right lengths compared to each other, right? Right? If one force is 3 newtons and the other one's 6, then the 6 newtons should be twice as long as the 3, right? So then you're going to very carefully draw this, and then you're going to sketch in the resultant, and then you're going to literally measure how many centimeters this is and turn it back into how many newtons it is using your scale. And you're going to measure experimentally with the protractor what angle this is. Right? So you're going to have a chance to try this out. but it's going to be like a little experiment rather than thinking of this as like trying to solve it by some weird geometrical theory. So let me kind of telegraph the answer. We're going to have that it's so and so many newtons at so and so many degrees, and that's probably best measured again from the horizontal. Now, even though I have just drawn a sketch where I definitely haven't been paying attention to trying to make it a scale drawing, I can still get some idea of what the answer should be. Because we know what is the very most that a force that could be achieved by these two forces, individual. How much net force could we possibly hope to get out of these two? 7, right? We're not going to get more than 7 no matter what we do, because if they're pointing the same way, exactly, you'll get 7. If they're pointing exactly opposite, you'll get 1. So that's the lower bound, right? So we have a bound. It's going to be somewhere between 1 and 7. We did something horribly wrong if it's bigger than 7 or lower than 1. In fact, I'll go one better. We saw that if they were pointing 90 degrees, then it was somewhere in between, certainly. We found it was 5, right? 5 newtons? Are these guys, in this case, are they pointing more the same way or more opposite? Same. So I'm going to say that the answer should be somewhere between 5 and 7, right? It should be bigger than 5, because 5 was when they're perpendicular, and these aren't perpendicular, they're actually more the same way, but it shouldn't be as high as 7 because, of course, they're not exactly the same way. They're just kind of generally in the same direction, right? So somewhere between 5 and 7 is where we should land, right? Does that make sense? Okay. Let's talk about the angle. One pulls at 30 degrees and the other one pulls at 60 degrees. We should get something between them, shouldn't we? So we should get somewhere between 30 and 60 degrees. What's halfway between 30 and 60? 45. Can anyone tell me why where we should land relative to 45? Towards 60, that's right. Why?
It's 4 newtons compared to 3.
That's right. There's a bigger influence. That's right. So 4 newtons is a larger influence than 3 newtons, so that angle matters more. So once again, we talk about when something matters more, and we conclude that it should be somewhere between 45 and 60. That's not bad, considering we haven't really even started. We're just kind of telegraphing just intuitively where the answer should be. I can go ahead and draw it in, by the way, over here if it helps to see it not head to tail. It's going to be something like this. I tried to draw it a little closer to the 4 Newton force in terms of angle. I don't think I did a good job with that. But generally, if you have two forces that are diagonally up and right, it should not be a surprise that I get a net force that's big up and to the right. Okay? All right, so let's go ahead and look for these features in our diagram. They're there. Now, look at this. If I went here 3 newtons and here 4 newtons, that would be a length of 7, right? But this is a little bit of a shortcut, right? So this is going to be slightly shy of 7, right? Because this length is 3 plus 4 is 7. This is takes a little bit of a shortcut. It's going to be a little shy of 7. It's there. Thumbs up. Let's look at the angle. The angle is certainly bigger than 30, isn't it? Right? So if this is 30, this is bigger. But it's not as steep as the 60. So it's somewhere not as steep as 60. So it's all there in the construction. The only thing we need to know is how do we go about actually doing this, executing on finding the exact values in a simple way that will work if we have 2 forces or 17 forces. And that's through components. Components save the day again. You saw in homeworks number 3 that components are your lifeline. You have these complicated motions. If you have components, you can sort a problem into an x bin and a y bin and just do them separately. Same thing here. So what I'm going to do to show you this is go ahead and draw in the components of both of the vectors, the individual vectors. So here's my 3 Newton force, this far to the right, this far up. So I've drawn in the components of the 3 Newton force. I have an x component, F1x, and I have a y component, F1y. There are my components of the first force. Let me do it for the second force. This also has a rightward component. Oh, I shouldn't have used red. Well, that's all right. Well, let's see if I can get some blue. Blue seems to be going okay. There are my components for my second force. X component, y component. So where am I going with this? Hopefully it will become apparent very shortly. I've drawn in the individual components of the forces and the individual forces. Let me also draw in the x and y components of the net force. So here's how far the net force is to the side. Here's how far it is vertically. F net x component, F net y component. So I basically turned everything, including the individual forces and the net force, into x and y components. Now, here is where I will point out that the components carry all the information in the entire vector. So if I added in the components, I can take away the vector itself. This is something you might not have as much access to doing, but I have an eraser which I can easily use. You might not be able to do this, but you can hopefully still appreciate the diagram once it's left. So basically I've got everything turned into horizontal and vertical lines, right? Now check this out. F1x plus F2x gives me F net x, right? You see that? This plus this gives me this. So here I found my prescription for vector addition. If I want to find the net force x component, I add up the x components of my individual values. It's a very simple prescription, and it works if I have 2 or 3 or 17 different forces. I line up their x components, add them up, and I have my net force x component. That's a simple prescription that's incredibly straightforward. If you didn't catch it quite, let's do it again with the y direction. If I want f net y, I add f1y, f2y, right? This y component plus this y component is this. So same thing with the y direction. I take my individual y components, line them up, no matter how many I have, I get f net y component. This is such a straightforward prescription that oftentimes, or in fact I should say, from now on, I won't even bother to draw them head to tail. I won't even bother to do the graphical method. The graphical method was my in to show you how components would do the job for us. But because this is so straightforward, I don't actually need to put them head to tail. I just remind you that this was just to show you that components can give an incredibly straightforward prescription on how to do this. If you know how to break a vector up into components, so one of the individual vectors, right, you can find the x and y components. And then if you do it for your entire list, line up your x components, you'll get something when you add them. And when you line up all your y components, you add them up and you get something, okay? So let's go ahead and do that for us, okay? Are there any questions before I erase a little space? All right, so let's try it out. So let's do vector addition by components. So the comps method. So I guess first of all, I'll go ahead and put down my first force, 3 newtons, 30 degrees. Let's go ahead and just get its components. So you should be able to do it this fast. Positive component, positive component. Size here, 3 newtons cosine of 30, 3 newtons sine of 30. Okay? If you spend 5 minutes on that during the exam, you're taking 5 minutes. You definitely should be spending on something else. Make sure you get the hang of this. Okay? So see that adjacent side? Throw it on hypotenuse times cosine. Make it plus if it's in the plus, minus if it's in the minus. Okay? Let's go ahead and just follow this prescription. Net force x component. Well, let's take one of our x components. We just got one. And the other one hopefully shouldn't surprise you, so I don't have to write it out. 4 newtons cosine of 60. So I go ahead and add that up, and I will find, that's a number, that's plus 4.6 newtons, round it off a little bit. And let's do the same prescription with the y direction. Add up all our y components. The cosines just change to sines. You do this, get around 5.0 newtons. 5.0. Okay. So just that easy, we now have the properties of the net force. Of course, these are the components. Notice how we have to go back and forth upon every problem, right? So we had to break up the individual forces into components to get the net force components. Now we want to reassemble. Okay, how do we reassemble again? How do you get the size of the net force if you have the components? What is it? Pythagorean theorem. So 4.6 squared plus 5 squared, square rooted. What are we going to get? 6.8 newtons. Is that number where it should be? Between 5 and 7, isn't it? Right on the target. It's a little shy of 7, right? Because while they're generally kind of in the same direction, right? They're not exactly in the same direction. How do we get the angle? Inverse tangent, right? Inverse tangent of opposite over adjacent. Okay? So what do we get for that? Try it yourself. 47 degrees. Right on the money. It's somewhere between 45 and 60. Okay? This is how we do vector addition. We go ahead and we do it by components. It's an incredibly easy thing to do, but it does require that you can both break up vectors into components as well as reassemble them at the end. Okay? I should mention, by the way, that oftentimes we don't bother to reassemble the components because we're so used to keeping the two tracks, right? We learned in homework 3 that having an X bin and a Y bin is the most powerful way to attack problems, right? So in fact, what we do is we acknowledge that the X component of the net force actually causes the X acceleration, and the Y component causes the Y acceleration. Okay? So if the X and Y directions are independent, then any X net force causes the X part of the acceleration, and then the Y part of the net force causes the Y acceleration. Now this statement right here, you can represent it mathematically in a certain way, and that way it looks like this. So you can see that the F net equals ma is there, right? This is the entire net force, causes the entire acceleration. And then here, what we see is the forces added to each other. And this notation is a little bit of a booby trap because it makes it look like you can just add up the numbers for the sizes of the forces without any regard for direction. We, of course, know that that is wrong, generally speaking, except for in a single case. So if you see addition, but the quantities have the vector hats on them, think vector addition, okay? And the easiest way to perform the vector addition is by splitting it off into x and y tracks, okay? So when you see any of this, think 2 tracks. Think components. Components are your friends. Are there any questions on this before I move forward? Yeah. That should be Pythagorean theorem. 4.6 squared plus 5 squared equals 6.8 squared. So again, if you're reassembling a vector, Pythagorean theorem is how you get the magnitude, and inverse tangent is how you get the angle. Does that make sense? Does that not come out to, doesn't 4.6 squared plus 5 squared equal 6.8 squared? Yeah? Okay, and then inverse tan of opposite over adjacent, inverse tan of 5 over 4.6 should give you 47 if your calculator's in degree mode. Again, that's stuff that I talked about previously. So if you don't know how to break up vectors into components or reassemble them, make sure you get those skills up. Was there another question over here somewhere? Okay. Okay, so the only order of business left for the rest of homeworks 4 and 5 and the entirety of exam 1, which I will be probably announcing the 2-week advance notice this week. The only order of business left, besides obviously Newton's third law, which I'm holding off on, is to now just learn about individual forces. So we're going to introduce 4 of them total for this exam, 3 of which are on the next homework. Let's do it. I'm going to introduce 2 of them today just because I need at least 2 to play around with. Otherwise, there's no vector addition that I can have, right? The force of gravity, also known as weight, is the first one. And of course, since force is a vector, we need to discuss size and direction. And the second is tension, which is the force from a rope or a string. Rope or a string. And that, again, its forces have size and direction, so we should discuss what are the rules for how those tend to act. All right, so first, before I do anything else, let's talk notation. This is the same vector notation I said I would stay true to till the end of the course. If I want to refer to the force itself in its totality, including both size and direction, I put the vector hat. If I want to refer to just the size, then I leave the vector hat off. Same thing with tension. T vector is the whole thing. T is just the size. I should also let you know that the force of gravity, it's another name for it is weight, so sometimes you will see it as W. Okay, so if you ever see a W vector, that's what it is. I won't use it, but I want to make sure that if you ever see it anywhere else, you're not totally blown away. And of course, just the size, W, with no vector hat. All right, so let's talk about rules of thumb. Force of gravity, direction, downward. That's the most generic way I can think of to describe it. I notice a lot of people on homework want to say that downward is negative, which is only true if you've picked up to be positive, okay? There's no universal negative axis in the universe, okay? So downward is a generic way. If you want to pick upward to be positive, then downward can be negative. If you want to pick downward to be positive, then downward is positive. And as we will see, we will have some very bizarre choices. Sometimes we'll pick the y direction like that. Why would we do that? It'll become clear. But then gravity is not positive nor negative, okay? Gravity is downward, right? What's the size? Well, this is where we have a little bit of a cop-out, because we don't really know what gravity is all about yet. We won't actually get back to that until past exam 1. It's actually going to be on homework 6. Right now, the force of gravity is going to be the force that causes the magic acceleration. So all I've done is made Newton's second law, F equals ma, compatible with the fact that we somehow know gravity causes this acceleration for everything, right? That doesn't answer anything. It just makes our previous statement that gravity has a constant acceleration compatible with F net equals ma, right? In fact, it actually brings up more questions than it answers. Let me explain. Now, if we had two objects, right? One that's a small mass and one that's a big mass, right? And we talked about what would happen if we applied the same force to both of them, right? We put the same amount of effort into both of them. So we can put in F, right? Are they going to accelerate the same? No. Which one has a smaller acceleration? The big mass, that's right. So we have that this one is less stubborn to motion. This has more mass, it's more stubborn to motion. The acceleration is smaller, right? That is not what gravity does, okay? So this is when the force is the same on both. But here's what gravity does. Gravity will take a small mass and a big mass, and it will accelerate them exactly the same, right? 9.8 meters per second squared, right? So I could draw in the acceleration is the same, right? So we are forced to conclude if this is going to be compatible with Newton's second law, what does that mean about the force? Which one feels a bigger force? The bigger mass, right? If we're going to take that big hunk of mass, which is that much more stubborn, and we're going to make it accelerate exactly the same, gravity somehow has to know to pull harder on it. So the force of gravity is not the same here. So Fg must be larger on a larger mass. It's right in the equation, by the way. Look at the equation, right? If that's the equation for the force of gravity, if this is fixed for everybody, then a larger mass apparently feels a larger pull. How does gravity know? How does gravity know to pull harder on things that have more mass? That mystery will remain a mystery for now. But gravity somehow knows. If it's going to accelerate everything exactly the same way, it somehow has to know to pull harder on things that have more mass. Strange, isn't it? So we'll get to how gravity knows to do that. But for right now, our equation is completely just what we call ad hoc. It's just kind of something that'll work. Okay? Like a lot of students, they make up ad hoc equations. They just make up stuff and try to use it instead of using the stuff I talked about. And sometimes it works, maybe, but then it doesn't work somewhere else, or it doesn't work at all in the first place. Okay? What we're doing here is the weirdest kind of thing. We're just basically working backwards to inferring the force of gravity by knowing what acceleration it causes. Okay? We don't know anything else about the gravity that we didn't know before. We're just making the little that we knew before, which is that gravity causes a constant acceleration, and we're trying to make it compatible with Newton's second law. In fact, This is such a weird thing that we kind of use it in situations where it almost seems like it'd be a bad idea. We're basically saying that the force of gravity is the force that causes the magic acceleration. That is as yet undetermined why that is. Okay? We'll even use it in a situation like this. We have an object that's not in free fall, it's sitting on a table. Okay? Now that is not accelerating at 9.8 meters per second squared. In fact, if it's just sitting there, what's the acceleration? 0, right? It just stays at rest. And yet, if the table weren't there, it would be accelerating at 9.8 meters per second squared, right? And so here's what we say, is that we can infer the force of gravity, right? Gravity, of course, is still there. It's still pulling. We infer it by the acceleration it would cause, even though that acceleration is not what it actually has, right? So the reason, of course, it doesn't have that is because there's a support force from the table which kills it. But what I want to point out is that even though the acceleration is really 0, we still use that to figure out the force. It's like a weird thing. We say like, well, this is what the acceleration would be if the table weren't there, so we're going to work out the force from that, right? It seems almost silly to still be using the g, even when the acceleration is not that at all. But it's our only way to figure out the force of gravity at this point, okay? So make sure you understand why that's not somehow contradicting itself. If we work out, let's say it's a 1 kilogram mass, right? The amount of force required to accelerate a 1 kilogram mass to 9.8 meters per second squared, that force is 9.8 newtons. And we, of course, say that gravity still pulls down with 9.8 newtons, even though there might be a 9.8 newtons upward to kill it, and the acceleration is actually nothing. Okay? So that's kind of what we're doing there with gravity. We'll come back and understand gravity in more than just kind of a patchwork ad hoc way later, but this will serve us for now. Okay? Are there any questions on that? Okay, so that's one force right there. Let's talk about tension. Tension from a force from a rope or a string. Here's a string I can use. Okay? Now the amount of tension in a rope can vary. Okay? It can have no tension at all. I can tighten it, have it more tension. I can tighten it some more. The tension can increase from there. There might even be a tension at which the rope snaps, right? And we can't go above that. So as long as we stay below that, the tension can vary, right? Anywhere from 0 up to the breaking strength. And it can be anywhere in between depending on the situation, right? So it can be tight or not tight depending on some other considerations. So as far as the tension goes, the size varies. There's no magic bullet, okay? It depends on the situation. However, there is one thing about tension in terms of the direction that's important. Now, a string is very effective in pulling on something like that, right? I can pull it. But you can't push something with a string, okay? There's an inherent one-wayness to a force from a rope or string. So that has implications in our problems. So let me draw an example. If we have some kind of mass, we have some kind of rope attached to it, like this. A rope always pulls, never pushes. So we expect to see that the tension always pulls and never pushes. It should never be like that. So make sure that the tension points away from the object. So always pulls and never pushes. That's an important rule of thumb for the tension force. Okay, so there are 2 forces so far. We'll introduce 2 more. The normal force or support force from a surface, that'll be on homework 4. The frictional force, which will be on homework 5. But right now, 2 is the minimum I need, so I can add some forces use my vector force addition ideas. So let's go ahead and jump into a problem. These problems is usually where, if you don't watch out, you can get totally blown away at this early stage of the course. So make sure that you're really careful in being able to follow what I'm going to do here. What I'm going to do is I'm going to first just do a problem so you can get a flavor for what it's like. And then, probably not today, but next lecture, I will write down a formal forces problem-solving strategy that you can follow step by step, a 6-point plan to get through these problems which can otherwise seem very overwhelming or unclear what to do. Okay? I don't want to write that strategy down right now because if I just write it down without having any sense of what it's for, it's going to look too abstract. So let me do one problem first, and then when I write down the formal strategy, you can go, oh, okay, yeah, we did that. That made sense. That got us the answer.